Okay, so let's start. Is the screen visible?
Yes, yes. Yes.
Yes. Oh, thank you. Let's start. So this is week number 10. Before we start, any questions from previous session? Okay. If not, then let's proceed. So this,
Can you just
yeah.
describe last week's question number 5?
Okay. Question number 5 of the assignment. The one that I discussed or in your
No, no, no.
course?
The question which was assigned,
Okay. It's
yeah,
okay.
week 9.
Yeah. Let me open the course page. Question number 5. This one?
Yes.
Okay. So did you try to solve it? What happened?
The answer is not matched. I gave answer that one. They're not showing. First in the group they told like this question is wrong. Like the not question is wrong. The options are wrong. But uh, when they declare the result in that they are saying one of the option is correct. So mine is wrong.
Oh, okay. Then let's do it. What answer did you get? Was it close to one of these or totally off?
No, no, no. It's quite different from this.
Okay. Let's first do analytically, okay? Just to check. So the equation is this. Kappa is 0.5 and T is 1. So this is question 9. Question 5, week 9. Solve. And del psi by del t is equal to kappa del 2 psi by del x2. Okay, kappa is equal to 0.5, t final is 1, dt is to be taken as 0.001, and psi 0 of t is e minus x minus 2 square. Was there any coefficient? Let me just check. Minus 2. Okay. Oh yeah, we can't do this analytically. Wait. Maximum value of this. I mean, we can do, but we need that formula. So let's just plug this in the previous week's code. Week 9, right? It's this one, right? The only difference is that you have x minus 2 here.
Yeah.
That should not really change the answer, should it?
Kappa is 0.5.
Ah, okay. Yeah, that's right. So let me just copy paste this in a new. code block. So where is kappa? Kappa is 0.5. Okay, this is week 9, question 5, new course. Kappa is 0.5 and this is x minus 2, although I don't think it will change anything. And the box is still 0 to 2 pi, right? Let me just confirm. Box is 0 to 2 pi. And this gives the maximum value of f. Now, let me run the numpy. 0.4471.
Yeah, this one I exactly got this answer.
Okay. Use 3-point central difference to calculate second order and RK2. It's the same, although it should not change the answer too much.
I also got the same thing.
Yeah.
I think that I got the wrong things again. I try with your code also by
Uh-huh.
copying that thing and again doing it, and try with the another also. Still, I'm getting the wrong answer. And again, my question is answer is get wrong for this.
So did you also get 0.4471?
Yes, same one for
Yeah,
me. Same.
yeah,
Okay.
same one, same one. One
Probably,
I got from my code.
yeah. Okay, let's try. We had done some theoretical calculation, right? Let's just check if we can do it for this one. I can't find it. Maybe it's there in the code itself. Yeah, it's this one. So it is this one, right? So maximum will be the coefficient of exponential because the peak stays there, it just goes down. So the location of peak, in this case it's pi, so it will be pi because then it will be exponential of minus 0, which is 1. So let's let me print this number where sigma sq needs to be calculated. It's the same form, so it should be the same 1 by 4. And T final is 1. And T final K is 0.5. Point 4472. Yeah. So it's probably mistake from their end. So I'll let them know. All right.
Thank you.
Yeah.
Thank you.
Okay. And last time I tried to explain this formula, and you can look it up online also. So how the diffusion occurs for an initial Gaussian profile. It stays Gaussian, but the standard deviation increases. So using that, you can actually find the answer. Okay, so let me just write. So this was -2 here, and this was x comma 0, and we had to find max of psi x comma df, which is 1, and the answer is about 0.4471. Okay, not given. Okay, anything else?
No, nothing.
Okay, sure. Then let's start with this week's content. So this week was all about, well, not all about, but mostly about root finders. So root finders, and I'll take a different route. So I'll first discuss what was called the relaxation method, and there is a reason why I'm doing that. And when is relaxation method used? When you want to solve equation that is of form something like this. Okay, f of x is equal to x, and algorithm is simplest possible. It is just that xn plus 1 is equal to f of xn. Okay, so you start with x0, feed it in f, get x1, now feed again f, get x2, and keep on doing that. After some time, what will happen? Maybe after 23 steps, x23 gives x24, but both of them are more or less same. Okay, within tolerance. And that means whatever this value is x star, that means f of x star is almost equal to x star itself. Yeah, because it gives the same answer. And then we say that if this is satisfied, it's called fixed point of the map. Okay, so this thing is called map. Okay, a discrete map, and the values of x which satisfy this are called fixed point. But the fixed points that we can reach via this algorithm are stable fixed points, right? So you know what is stable and unstable in case of equilibrium. If you have a potential like this, then this point is stable. What does it mean? It means that if you put a ball here, it will stay here forever, right? That's the definition of equilibrium. Well, same thing happens in this case also. If you put a ball exactly at maximum, it will stay there, right? But we can find this position by dropping the ball anywhere. So we can drop here, it will go here, and if there is some friction, then eventually it will find this stable equilibrium point. But what happens here? If I put the drop here, then it will just roll down, right? It won't find this equilibrium point. So this is unstable, this is stable. And we know the criterion, right? If this is x star, then we have force at x star to be 0. So the slope should be 0. It should be minima, and that means the second derivative would be positive. Okay, here again force is 0. So if you start exactly at that point, you are going to stay there. But even if there is tiny perturbation, it will fall off. So the second derivative is negative. So in the same case, for the map we can derive criteria. So stability criteria, criterion for map. Now, what does stable mean? It means that if you start from some x star plus some epsilon 0, then eventually it should go to x star, right? That's the definition. Where you start from around, it will roam around, but it will eventually find x star. Then you say that it's unstable. What will happen? It's stable. So if the arrow is like this, going into the fixed point, well, if you start from somewhere around and you just go to infinity, okay, and if you don't reach x star, then you say that this is unstable. So we can do something like this, that okay, our x0 is x star plus epsilon 0, then x1 will be x star plus some other epsilon 1, and we can calculate this epsilon 1 in terms of epsilon 0. Okay, then x2 is x star plus epsilon 2. So we can generate a trajectory. One trajectory is when we start from x star, then we'll just stay at x star, right? So in this case, this is iteration and this is x. So we are plotting x of n as a function of this n, which is number of iteration. So if you start from x star, you are just staying there. But now let's start at x star plus epsilon naught. So this is x star plus epsilon naught. Then either you can go away from x star. In that case, x star would be unstable. And if you go close to x star, then it's stable, right? So this is epsilon 1. Then this distance is epsilon 2, etc. So we want epsilon n going to 0 as n tends to infinity, right? So now let's calculate epsilon 1, which is x1 minus x star, right, from this equation. Let's move from 1, and x1 itself is f of x star plus epsilon 0. This is our x0, right, minus x star, and this we can expand, right? We all know Taylor expansion, f of x star plus epsilon naught times derivative at x star plus higher order term. Okay, this will be order of epsilon 0 square and minus x star. Now what is f of x star? This is equal to x star itself, right? By definition, x star is a fixed point. We don't know whether it's stable or not, but it is a fixed point. So it is x star plus again the same terms and minus x star, which gets cancelled conveniently. So we have epsilon 0 times f dash of x star. This is epsilon 1. So epsilon 1 is epsilon 0 into something, okay, which is this number. You can call it lambda or something. So if this number f dash x star is less than 1, that means epsilon 1 is less than epsilon 0, at least modulus wise, which means epsilon 2 will be less than mod epsilon 1. So in general, this epsilon n is going to 0, right? Which means it is stable. Okay, so that is the criterion, that the derivative at x star, the absolute value of it should be less than 1. Okay, so we can find solutions like cosine of x is equal to x, right? If you look at the plot of this, cosine x would look something like this. Starts from 1, then at pi by 2 it reaches 0, then does this in both directions. And x itself looks something like this. And you can prove that it has only one intersection point, which is the solution of this curve, right? So this is y is equal to x, this is y equal to cosine x. And this point can be found not analytically, and it's actually an irrational number, rather transcendental. But what you can do is start from any point, x0 can be anything, and keep on applying f, which is cosine. Okay, so you can in fact start from 69, then go to cos of 69, then cos of 69. If you keep on doing that, after 11 or I don't know 10 iterations, something like this, you will start getting a number which stays almost constant up to at least 3-4 digits. Okay, and that will be your this thing, the stable fixed points. Now why am I sure that it's a stable fixed point? Well, the derivative at x star will be mod of d by dx of cosine x star, right, at x evaluated at x is equal to x star, and derivative is mod of derivative of cosine is sine, so it is mod of sine of x star, which is definitely less than 1. Okay, so even though I don't know the number exactly, I know that it is stable, and there is only one stable fixed point, so I'm going to reach there, right? Okay, and now let's look at the second method, which was the first method that professor discussed, bisection method, and that was for finding the actual root of any function, right? And what was the idea was again divide and rule. So you let's say this is your function, so you start with 2 points, mm, a and b, start with a b such that a and b are on the different sides of the zeros. Now how can we write it mathematically? We can say f of a times f of b, this should be negative, right? Because one will be negative, one will be positive. It can be ulta also. Okay, the f of a is positive and f of b is negative, but the product will be negative. And then start dividing. So look at the midpoint of these two, call it c, and then the only information from the function comes here, and that is which interval to choose. You have to choose either this one or this interval, and it's the interval that contains the 0. Now how can we know which interval contains the 0? Well, again look at f of a times f of c. If that is negative, it means the this interval contains the 0, which means a will stay as a and your new b will be the c, right? So now your next interval is this one, and then keep on doing the same thing. So every time you are dividing your interval into half, so you are going to converge to the 0 point. Okay. And by the way, there is one assumption, which is that the function is continuous, right? Because you can have something like this. Oh, not here. Yeah. and then you can start. Your A could be here and B could be here, and no matter how close you will go to, you will not find 0 because it does not have 0, right? So, and that's a theorem also. It's called Bolzano's theorem or something like that. I'm not exactly sure if this is exactly identical to this, but you can look it up. It's called Bolzano's theorem. Okay, and there was third method, which is the star of the show, right? Newton Raphson. And that's very interesting, and it has a very different idea, which is that we'll start from any point, and you want to go in the direction of the slope, right, where it is going down, just like how the ball wants to go down. So you calculate the slope and draw a straight line, the tangent line, and wherever it crosses, that's your next point. Then again do the same thing. So after some time, when you get close to the 0 point, your line is almost straight, right? So in the next step, you go very close to the 0 point. That's why the convergence is very fast. Okay. So this is your x0, and this will be your x1. Okay, this is x0. This is f of x0. So you can calculate this tan theta. Tan theta is basically f dash x0, and that is equal to f of x0 divided by the interval x0 minus x1, which means x0 minus x1 is equal to f of x0 divided by f prime x0, and that gives us x1 is equal to x0 minus f of x0 divided by f prime x0. Okay, and this step is repeated again and again. So in general, xn plus 1 is xn minus f of xn upon f prime of xn. Okay, this is the algorithm for Newton-Raphson, and so if you see closely, stare at it, you see that it is a map, discrete map, right? Because it's of the form xn plus 1 is some function. Okay, we have used f, so let's call it g of xn. Okay, and g of xn is given by this xn minus f of xn divided by f of f prime of xn. Okay, so the functional form xn's are discrete, but if I look at functional form, g of x is x minus f of x divided by f prime of x. Now we can look at the fixed point of this, right? So fixed points of g, which is gx is equal to x, and we can solve this. Gx is this x minus fx divided by f prime x, and x is, well, x, so x gets cancelled, and that means f of x is equal to 0. Okay, which means zeros of f are,
Arsh,
yes,
you're writing something on a board. It's not writing actually. It gets
it's not
stuck
visible,
somewhere.
it's stuck.
No, it's only visible the Newton.
Oh, okay, I don't know why. Well, thank you for letting me know. Let me stop sharing and reshare it. Is it visible now? Can you see the screen?
No.
No. What about others?
It's visible for me.
Yes, we can see. It's
Yeah.
visible for me also.
Okay. Maybe you can
Your
try to
name
rejoin. Yeah.
icon name only over there. A, it's written over there. Only. Screen is a black completely.
Okay. Maybe you can rejoin, because if others can see, then it's probably issue from your end. Maybe it's internet or something. Others can see what I've written, right? Zeros of f, everything.
Yeah.
Yeah.
Okay,
So
I will
yeah,
do it.
please rejoin. Is it visible now?
No,
Still no?
I again join with the link again.
Okay, I think it could be internet or something. Let's wait for a minute. If she does not join, then we'll continue. Can you see the screen, Aparna?
Yes, now it is
Now it's
visible.
visible. Okay. So let me quickly go through over it. So you have probably seen it. So this was there in the class, that the algorithm for Newton-Raphson is this: xn plus 1 is equal to xn minus f of xn upon f prime xn. And then I said something new which was not there, that it is a map, because maps were discussed later on, right? And if you denote that map by function g, then the functional form of this function g is x minus f of x upon f prime x. And then we can find fixed point of this map g, which is the set of solutions of this equation g of x is equal to x. And then when you solve it, you get that f of x is equal to 0, which means zeros of f are fixed points of g. Alright, fp is fixed points. Maybe I should write. And what about stability?
What does it practically mean? Zeros of f are fixed points of G.
It means that if you want to find zeros of f, what you can do is run this map again and again, just like what we did with cosine, right? If you remember. So you wanted to solve this equation. So what you did was start with x0 is equal to some random number, and then apply cosine again and again. So xn plus 1 was cosine of xn, and eventually you reach a number. I don't know, maybe it's zero point 0.7 or maybe it's not, but whatever it is, it stays constant, and that will be the solution of this equation. Now what I am saying is that that was for f of x is equal to x kind of things. Now Newton Raphson is algorithm for solving the roots, right? F of x is equal to 0. So we can convert this into a map which is g of x is equal to x, g is not equal to f. Okay, g is a different function which has this functional form. Okay, and then we know we can find the fixed points. That is easy. Apply g again and again. Keep on doing that unless you converge to some number, and that fixed points will be zeros of f. Okay,
Got it. Yeah.
yeah. And the main surprise is this: the stability. So how do you calculate stability? You calculate the derivative of the map function, absolute value at x is equal to x star. Okay. So the derivative is d by dx of what is g of x? It is x minus f of x by f dash of x. Okay, and this is equal to d by dx of x is 1 minus f dash x. This is evaluated at x star, right? So this is already x star, and you calculate derivative of f. So this becomes f dash x star upon f dash x star, which is just 0. And so this derivative was basically the first order term in the Taylor expansion. If you remember this, it was this term, right? So x n plus 1, or rather epsilon n plus 1, the deviation was epsilon n times this f prime x star, and plus there was epsilon n square higher order terms, right? So now f dash x star is 0. If it was not 0, then what would happen? That epsilon n would go as this lambda to the power n times epsilon 0, right? Because, well, this is lambda. So it is multiplied, the lambda is multiplied every time to epsilon. So epsilon 1 is lambda epsilon naught, then epsilon 2 becomes lambda square epsilon naught, so on and so forth. And that's why when this factor lambda is less than 1, then this goes to 0 and we have stable solution. What happens when lambda is equal to 0? That means that this is almost 0. So epsilon n is 0 irrespective of n. Well, not exactly, because you have higher order terms that now you need to consider. But then you can prove that it will go as exponential of n. So it will be like, I don't remember the functional form. Let me check. It would be something like 2 to the power lambda to the n, something like that. Okay, which is much faster, which means it takes very less number of points to reach there, and that is the genius of Newton. Okay, because it is 0, this factor g dash of x, it has a fancy name, it's called superstable. So all the zeros of the original function f, which can be whatever it is, are super stable fixed points of this map G, and that's why the algorithm converges to the fixed point or the zeros of f very fast. Okay, it's faster than exponential. So and if you didn't understand, just take my word for it that that's why the reason is that it is a super stable fixed point, and that's why it is very fast. Okay, and there was another method which was called secant method. So this is number 4, right? Which is same as Newton, but I should write Raphson also. Should give credit where it's due. Same as, but we don't know the derivative at n. So we approximate it as, how do we approximate? Well, we have xn minus 1 and xn, so we say it's this backward difference, if you remember. Okay, so obviously now you are doing some approximation, so you are going to be slightly worse, but when you don't have the functional form or calculating the derivative is not possible exactly, then you do this. Okay, so if you want me to write, I can write the equation, the algorithm. It's xn minus f of xn, and here earlier it was f prime xn, this thing. Instead of that, I'll write this thing, f of xn minus f of xn minus 1 and xn minus 1. Alright, and these methods don't always converge. Yeah, professor had shown some kind of example where it was like this. So you start with from this point, you want to go here, so you draw a slope something like this, but the tangent is crossing this farther from the original point. Okay, so you go far from this, and now you start from this one. This tangent is almost parallel to x-axis, so you go even farther. So this was your 0. You started with x0 in hope of finding this location, but you went farther and farther. Okay, and if you do again, then you will see that x3 is very far. Okay, so your solution does not converge to any point, and it might not work, but when it works super well. Okay, and anything else? Yeah, and there was, I think, couple of lectures with boundary value problems. For OD, right? And the idea is simple. So there was one example which I really liked, which was pendulum, because we can imagine it, right? And the equation is d2 phi by dt2 is some minus g over L sine phi. Okay, and generally what we are given is phi of 0, the initial angle, and phi dot of 0, the initial velocity, are given. In that case, we know how to solve it, right? Runge-Kutta, Euler, and Louis-Frog, whatnot. So this is the ordinary thing. What was it called? It is initial value problem. This is essence of determinism, by the way. That you give me what is happening initially. So you have to give me where it is. You have to give me how it is moving, right? Because it could be going backwards. So just from the photo, you cannot predict future. But if you give me the photo of the pendulum and tell me how fast it is moving, then I can tell you what exactly will happen in future. Okay, then phi of t is exactly known. And why is it that only these two are needed and not anymore? That's because all the Newton's equation are of order 2. Okay, and that's basic fact of the universe that we live in. That's why Newton's laws are very important. It gives us that all the motion is happening up to the second order. Okay, then of course if you invoke many degrees of freedom and coupling and everything, then you can have higher order terms. But the basic motion, the forces are applied, those are of the form d2x by dt2, and that is what Newton observed. And again, that's the genius of Newton. Okay, but we are not doing this. What we are asking is that we have a pendulum and initial position, let's say it's 0, and it's a puzzle kind of thing, that after 2 seconds, this is at 0 second, after 2 seconds it's here. Then can you tell me where will it be later on or even at intermediate times? Then we have to find phi of t. So now phi of 0 is given and phi of some tau is given. Okay, and this you can think, right? So phi of 0 is given and you have some initial velocity which you don't know. And how can you do this experimentally? Well, you start with 0 velocity, but then you don't move, so you don't reach there in 2 seconds, so it does not work. Then maybe increase the velocity, so give a higher force, technically higher impulse, and see how much it goes, and at 2 seconds does it reach there or not. If it reaches just here, then give even higher force, and then you find out that it reaches here, so you overshoot. So you give somewhat like an intermediate value, and slowly you can find out what exactly the initial velocity, the impulse is needed in order to reach this exact place at this exact time. So that is what you do. You start with phi of 0, this could be this one, and this is your t, and then you assume that the initial slope or the velocity in this case, oops, this is phi, is something, and try the experiment. Well, you don't have to do an experiment, you can just run the simulation, right? Because if phi dot 0, so basically phi dot 0, which is the slope, is a parameter that we don't know. We can think of it that way. Okay, and then predict phi of tau, and it's somewhere here, but the actual given value is this. So you gave it less velocity than it needed, so you go higher. Okay, and then you discover that you overshoot. Yeah, so this is overshoot, this is undershoot. So your next guess should not be this or this, right? It's a common sense, it should be somewhere in between. So you go exactly at the middle and see again what happens. Maybe it overshot, then you go in the middle of this and this, which is this one, and that's very close to but slightly undershot, so you again go middle of this one. So we are going in the middle of this, right? So every time we are taking the midpoint of some two values, and what is that called? Well, that is bisection, that we already learned. So this is bisection method on this slope, the initial slope. And again, what is the assumption? Assumption is this phi of tau is continuous function of phi dot of 0. Okay, which need not be the case in general, but mostly it is, and that's why this works. Okay, so now let's do some coding questions, shall we? Any questions so far? Okay, then let's do theoretical questions first, very quickly, then we'll jump to coding part. First one, uh, in the answers in the chat box. Which is the most efficient method to find the roots in least number of steps? Bisection, Newton-Raphson, relaxation, or spectral method? Answers in the chat box. Bisection, Newton-Raphson, relaxation, or spectral? Yes, yes. Okay, that's Newton-Raphson 2. Let's see. Tanuja and Dipankar. Yes, that is the correct one. Yeah, we saw. This works every time but slow. every time, but slow. Yeah, it's like fixed deposit in bank. You get very small amount of interest, but it's not risky. This one works mostly, but sometimes it does not work. But whenever it works, it's fast. Yeah, it's like share market. Okay. Relaxation is for not finding the roots. It's for the fixed points of the map. And spectral method is something else. We have discussed about spectral methods, right? Okay. Choose the correct answer for the necessary condition for the convergence of this with the relaxation method, which is map. Okay, so we just discussed this. Is this derivative less than 1, mod of derivative greater than 1, mod of f of x less than 1 or greater than 1? Answers in the chat box, please. 1, 1, yes. We just did that, right? Why? Because epsilon n is this thing at the fixed point times epsilon n minus 1. So if it is less than 1, then this is decreasing, the perturbation is decreasing, and we are converging to the solution. Okay. So here it should be given that x is a fixed point of the map, but that's all. Okay, third one, write a Python program to find the roots. This we will do later.
Arsh, can you show me that above screen because I get
This one,
disconnected.
this one.
Uh, Question number one is
Question number 1 is
I
this
didn't
one.
see it.
Which is the fastest method to get the roots?
Okay, it just started now for the question answer session.
Yeah, it has just started. So we discussed first two. First one is which is the fastest method, most efficient one to find the roots in least number of steps. So that is Newton-Raphson, right? We even professor has discussed, and so that is the fastest, but sometimes it doesn't work. Bisection always works, but it is slow. All right. And the second one was the condition for the convergence of this discrete map with the relaxation method, right? And we just discussed it's that the derivative, absolute value of derivative should be less than 1 because that's the coefficient that is multiplied to the perturbation every time. So if this is less than 1, then it slowly goes to 0. So there is no perturbation at the end and it converges to the solution. Okay, just give me a moment, I'll plug the charger. Yeah, okay, so the third question is programming question, which we'll do later. The fourth one, how many number of computation is required to find the determinant of n cross n matrix? So there are some questions on matrix and linear algebra. I don't know, it was not discussed. Maybe they wanted us to do it on our own. So let's do it. So how do we compute determinant? If it is 2 by 2, then it's easy, right? The cross multiplication, it is AD minus BC. So we did 2 multiplication here, 2 multiplication here. Yeah. Well, what if you have 3 by 3? A, B, C, D, E, F, A, B, C, D, E, F, G, H, I. In that case, we know this result, right? We can break it down. A times this determinant, so E, F, H, I, then plus B times, we have to go circularly, right? So from B, we have to start F, D, I, G. Some people like to write it as this, minus B times D, F, G, I. It's the same thing, okay? And plus C times D, E, G, H. Okay, so now we have 3 multiplications, and 3 times the multiplication for each of the determinant, which was like 2, right? Order of 2. So I hope you understand this big O notation. Order of n cube, for example, it means that for large n, it is cubic. So the most dominant term is the cubic term. So we don't know what happens at small n, but as we grow n larger and larger, it is cubic with some coefficient, right? And there is a technical definition, but this is the idea. So if it is logarithmic, then it means for large n, it is bounded by log n, or it is log n. So if we have something like n to the power 4 plus 3n square, this is also order of n4, right? Because the largest term is n to the power 4. So we can show that this thing is always less than some constant k times n to the power 4 for n sufficiently larger, and that means it's order of n to the power 4. Okay, that's how it's done. So now we have 3 times 2 multiplication, something like this. Okay, we can ignore the constant coefficients, but the multiplication is looking like this. So now imagine we have n cross n entry. So A11, A12, all the way up to A1n, and then A21, A2n, and all the way up to AN1 to ANN. Okay, and this can be broken down into A11 times this matrix, which is this block, right? So determinant of this. And what's the dimension of that? That will be n minus 1 and n minus 1, right? Plus A12, again n minus 1 cross n minus 1 matrix, so forth. So how many such are there? Multiplication and such multiplication, and for each of them you have, well, you can go inside and inside. So n minus 1 multiplication, then again n minus 2 multiplication, etc. So it's order of n factorial actually. Okay, and if you look at just the first term, then n minus 2, and how many such terms are there? Well, n, right? So that is going to be n to the power n. So these are almost same. The closest answer that I could think of is n to the power n. Okay, and we are kind of using some properties of determinant to write this way. If we blindly multiply each term, like the first is this cross, okay, then the second is a12 times this, and this, what should it be? Yeah, like this. Then the third will be, even for each of them you do multiplication in all the direction, right? So if you do such naive computation, you actually get n to the power n. If you
Um,
yeah,
but if we see whatever example we have taken, three by three matrix A B
hmm,
C D E F G H I.
yeah,
That matrix, when we solve that, it is three. First is the third order, and means first is n, and second term will be n minus one, E F H I, when we take two.
yeah,
So if we take n into n minus one, that satisfies the thing. But if we take n square here, in case of three, n raised to n, sorry,
hmm,
so that is not applicable here. No? Means that is not matching with what we are selecting. Uh,
we are selecting n to the power n, and it's a
means
order notation. So small n, for small n it need not work, right?
okay, okay.
Yeah, it's different than saying this is equal to n to the power n.
Got it.
Got it?
Means because it is a big O notation, we can say that it is n raised to n.
Yeah. But what I'm trying to say is that there is a naive way of calculating this also. In that case, it will be exactly n to the power n, because you are going to multiply every time you take one of these three. So this, then you have to take one of these three. So that is 3. And then you take one of these three. That is 3. So at max, you get 3 times 3 times 3, which is 27. But more importantly, it's 3 cube. Okay. Now, what's the issue? Well, you are not going to use A times D times H, something like this. So there are some permutations which are not allowed. That's why it is not exactly 3 to the power 3. It will be something less. But that's where this notation comes in. That at max it's going to be order of n to the power n. Okay. So did you get it?
Yeah, no, got it.
Okay. Okay. Now let's do this one. What is the number of multiplication required during the elimination in Gauss elimination for solving n cross n matrix? Okay. And even I had forgotten what was Gauss elimination. It's not really that difficult. You have some equation like 2x plus 3y plus 5z is equal to 6, then something x, something y, something z is equal to something else, then again third equation, something else x, some y, some z is equal to something else, and you want to solve it. So you can write it in the matrix form, right? There are three numbers, so 3 by 3 matrix times x, y, z are your three numbers, 6 something and something. Okay, these are like 2, 3, 5, etc. And Gaussian method works this way. Let's say this is, I don't know, 1 1 1, and this is also 1 2 and 2. So the first step, so what we want to do is convert this into upper triangle, convert this to upper triangular matrix. Okay, so you have some numbers here, here, but these three numbers become 0. Okay, in general, if it is n cross n, then diagonal elements are okay, and elements above the diagonal, they can be non-zero, but elements below the diagonal have to be 0. That's Gaussian element. So we can, by the way, write it like this: 2 3 5 1 1 1 1 2 2, and then 6, and if this is 7 and 8, 7 8. And then we want to make this one 0 first. Okay, because that has to be 0, right? So how do we do that? Well, we say that second row is going to be second row minus half of the first row, because we want to get this to be 0. So now what will it be? 2 3 5. Now we subtract half of 2 from this, so it is 0. Then subtract 3 half from 1, so minus 0.5, and subtract 5 half from 1, so minus 1.5, yeah, is equal to 7 minus half of 6, which is 3, so it will be 4, and then 1, 2, 2, and 8. Then we do another operation to get this one as 0, so again R3. For that we have to subtract again half of this, right? So half of R1, so we get, don't worry, I'm not going to solve the entire thing, and this is 0.5 minus 1.5, this is 0, and 2 minus 3 half, that is 0.5, and 2 minus 5 half, which is minus 0.5, this is 6, 4, and 8 minus 3, which is 5. Okay, and then we have to do the one last step, which is to make this one as 0. For that we have to do R3 going to R3 minus
R2 plus R3 also is okay.
R2 plus R3. Yeah, we can do that also. Yeah, that will be better actually. Thank you. Okay, so 2, 3, 5, 0 minus 0.5 minus 1.5, and this is 0 as 0 plus 0, then minus 0.5 and plus 0.5, so this is 0, and sum of this two is minus 2, and now we got this thing. So this is called Gaussian element, and here we have three numbers, whatever they are. Okay, and why are we doing that? Well, now we can just read off the solution. So this is going to be Z if I did it correctly, which is very doubtful because I just cooked up a problem, so I don't know. Maybe I made a mistake, but that's not the point. Z you can find. Now this is a combination of Y and Z you already know, so you can find Y from this. And this is a combination of X, Y, Z, and you already know Y and Z, so you can find X from this. Okay, now the question is how many multiplications are you doing? So in this case, we did 3 multiplication here, yeah, because we multiplied by half here, then 3 here, and how many? 3 here. Okay, so we did 3 times 3. Wait, is that correct? That's right. Now imagine we are doing the same thing. So, but we have n lines. So 1, 2, all the way up to n. So first,
This will be 4 4 because we are taking the B matrix on this side and that multiplication also we are doing or not doing.
you are actually right. This will be 4, but let me write 4 as 3 plus 1. Okay, and there is a reason because we want to do with n. So for each of the entry n, for the first one to get the second one to 0, first we get the second one to be 0. We need n entry. Okay, now to get this third one, we have to do this one and this one. Okay, so we'll get n minus 1. And all the way, how many times are we writing this? That's the question. Plus 1, last one for the n one. So this is n minus 1 by 2 or n plus 1 does not really matter. So this is order of n square. Okay, and this you are doing for each of the row. And so you multiply by n, and this becomes order of n cube. Now this is not equal to n cube. We are not doing n cube multiplication. Alright, we are just, maybe the correct form is 1 by half n cube plus 3n square plus some constant. It could be n, because here we are doing multiplication, right? But every time we are multiplying n entries here, we are multiplying 1 here. So order of n is greater than order of 1. So that's why we can ignore this one. Okay, because it's going to be 1 no matter how big n is. So as n grows larger and larger, this can be ignored. Okay, so the correct answer is order of n cube. You can convince yourself later if you are not yet convinced. Just do this once and see how many computation is required, number of multiplications. Alright, then the sixth one is Python, seventh is Python, eighth one is not to Python per se. Choose the correct eigenvalue of the matrix. So this, I think at least some of you can answer. This is a matrix and you don't really need to calculate this. If you stare at it, the eigenvalues should be clear. First option is minus 1 1, 2 minus 1, minus 1 minus 1, and 0 0. In chat box, 1 Dipankar, Tanuja is also saying 1. Yeah, so how did you do it, Dipankar?
The diagonal entries are the eigenvalues because it's a identity matrix. No, not identity, it's a diagonal matrix. So the
Yes,
diagonal entries would be the eigenvalues.
right, exactly. Thank you, perfect. So what's the idea? Idea is that diagonal matrix have the eigenvalues. Okay, for example, if you have something like 2 3 5 7 and all others are 0 0 0 0, then its eigenvalues will be 2 3 5 7, etc. Okay, and what would be the eigenvectors of this? Eigenvectors would be the unit vectors. Unit vectors along axis. Okay, those will be your eigenvectors. Okay, you can convince yourself. If you do the calculation, you will find exactly the same thing. And anyways, how do we get the eigenvalues? What we are doing essentially is diagonalizing the matrix, because once we have the diagonal matrix, we can read off the diagonal elements and those are your eigenvalues. So in this case, it's going to be minus 1 and 1. And by the way, Python has this package called lineal in the SciPy. Okay, and that gives you eigenvalues of any matrix, and we are going to do that. And there is one last problem. Choose the most suitable method to solve boundary value problems. Okay, so interpolation we have done, Newton-Raphson we have done, Lagrange method. Well, that is a method for interpolation, so I don't know what to make of it. And shooting method. Which one is the correct one? 4. Yes. Tanuja and Dipankar. Yes. Shooting method. Yeah, we just saw it. You shoot it with some velocity and see how far it goes, and you have a target fixed, right? That's what boundary value problem means. So if you go beyond the target, then you decrease the speed, do it again, and so on and so forth. Okay, now let's do some coding. Okay, so the first problem is find the roots of the equation. It's a cubic equation using bisection method, and choose the correct answer. And of course we have to know the tolerance, which is given to be 10 to the power minus 4. So let's start it. What we should first do, because it's a bisection method, first we need to give the left and right point, right? So for that we need to do some research on the function itself. Let's write the definition of x, which is, let me zoom in, return this function x cube plus 4x square plus 6x plus 8. Okay, and then we want to find the range in which there will be 0, because otherwise we cannot do the bisection, right? So we have to plot. So on x-axis we give some linspace and p dot linspace. I don't know, minus 10 to 10. Okay, it gives minus 10 to 10 with 100 points. And then plot x and f of x. Okay, just to find where 0 is, the range. And we see the curve. First of all, it is cubic, right? This is how cubic looks like. You have S kind of shape, and it can have multiple zeros, 3 zeros in fact, right? Because it's a cubic equation. At infinity it goes to plus infinity, and minus it goes to minus infinity, because this coefficient of x cube is positive. And 0 is somewhere in between, so we can work with minus 10 to 10, or we can zoom in a little bit. So we can first give it some y limit. So plt dot y lim minus 10 to 10. Yeah, sure. And so 0 is somewhere here, so we can actually draw the 0 using h lines. Plt dot h lines at 0 from minus 10 to 10, and let's give it some color red, and it should be dashed. Well, so this is the 0, and this is the point we are hunting. It seems to be between minus 2.5 and minus 5. Okay, so we know some range in which it will occur, and as we can see, there is only one 0, right? Which can happen for a cubic equation, because this just means that other two zeros are complex conjugate of each other. Okay, so now let's write the code. So let's define a bisection method. Bisection method. And what all do we need? First we need f, yes. Then we need a, b, the left point and b point, and tolerance value, right? How far do we want to go? Or rather, how close do we want to go? So before that, we need to give one condition, that it should not be on this, both the points should not be on the same side, right? So it gives this code, which is good. So if f of a times f of b is greater than 0, it means both are either positive or negative. So they are on the same side of 0, and then it won't work. Okay, so if that happens, then we print no root found. We can write oops, uh, f of a and f of b have same sign, and then we return nothing, right? Because there is no midpoint, there is no 0 inside. And otherwise we follow this while loop. Yeah, if b minus a is greater than tolerance, if b and a are close enough to some tolerance value, then we don't want to do anything, right? Just we can give either of them as the answer. So we can define this midpoint, which is c, but let's call it mid. Mid is equal to a plus b by 2, and then yeah, it gives the answer. Now we have to check which region the mid belongs to. So we first compute f of a times f of mid. If this is less than 0, then what it means is that mid is to the right and a is to the left. So we have to take a and mid as the next interval. So we change b to this mid value. And if that does not happen, then the 0 is on the right of the mid. So the right point, which is b, stays as it is, and the left point a becomes the midpoint. Okay, and then we return a plus b by 2. Okay, at the last step we can keep track of one number, how many times this while loop is run. Okay, so we can say I is equal to 0, not here, and every time the loop runs, I plus is equal to 1, and then we can return both the value, the 0 and I, right? That's the number of iteration. So let's run this. Okay, it's running, which means function is probably okay. Now let's give the value of a and b from the research, quote unquote, that we did earlier. Should be between -5 and 2.5, right? And if we want to be ultra sure, it's -5 and 0. So we can say a is equal to -5, b is equal to 0, and tolerance is 10 to the power -4, right? So we can write 1e minus 4. Well, just like how we write in scientific notation. This means 1 into 10 to the power -4. And then the root is going to be the bisection method of f of a comma b comma 12, and then we print root. But since we are returning two values, it gives off the root as well as number of iteration it took. Okay, so maybe I should print root of 0. Root is equal to, and another line, print iteration. It took this iterations is equal to, yeah. Okay, so it's -2.8812, and we can in fact round it off. Was it asked in the question? Yeah, round. But by now you probably know how to do that. Round this to 2 decimal points, which will be -2.88, and take 16 iteration. So in fact, I think that was the answer. Yeah, -2.88. Okay, pretty simple. And now we have this linear algebra questions, but most of it is already given what to do. So even if you haven't learned this, it should be doable. Nonetheless, these questions will help you. So write a Python program to solve the following linear equations using this linearc.solve function, and from SciPy module. So we'll import that one. This is the system. So this function will solve and give us the xy, and then choose the correct value of x plus y plus z, and round it off up to 2 decimal points. So let's first write the matrix. A is equal to, so the form is Ax is equal to B, something like this, right? So what is matrix? Well, it's an array of array, right? So you have three arrays and each array is a row. That please remember. So the first row is 3, 4, minus 1, 1, 2, 1. I'm reading the coefficients of x, y, z. Okay. And the third one is 5, minus 1, and 7. Then the b vector, that is what is there on the right x. That is 2, 11, and 5. And the solution is np dot. Okay, we can use np as well. This should ideally work. Let's just see. Yeah, np.linearc.solve also gives. And if you want to religiously follow what is given in question, then import this linearc from scipy. So you write from scipy, import linearc, and then you can write just linearc.solve. It will give the same thing. Okay, but what we are asked is x plus y plus z. So we need np.sum of this, which is 6.375. So if we round it off, round x to 2 decimal points, it will be 6.38. What happened? Oh, basic error. I round off the sum. 6.38. Okay, and that's the answer. 6.38. Okay. So this used to be a chapter in our 11th or 12th, right? Now we can do it in 2-3 lines. Just use np.linearc and we can almost do all the problems in that chapter. If you have any questions, just interrupt me and ask. Again, pretty much the same thing. Calculate the eigenvalues. Now we don't know how to calculate, but they tell us it's linearc dot eigen. Okay. And then choose the correct value of sum of eigenvalues and the product of eigenvalues up to 2 decimal places. So if you have done MMOP, mathematical methods of physics, you can do this without actually programming, right? So we'll do that later, but let's program. So let's import first of all from scipy, import linalg, that is linear algebra, and again let's write the matrix. So this is 2, 0, 0, and the second one is 0, 2, minus 3, and 0, 3, 2. Yeah, it already gives this. And then we are using linearc.ig, this function of A. So it does not just give eigenvalues, it also gives eigenvectors. So it gives a tuple with 2 elements. The first one is array of all the eigenvalues, the second is array of all the eigenvectors. So we can write eigenvalues comma eigenvectors is equal to this. So all the eigenvalues will be stored in this array and the vectors will be stored in this array. And then we can print the eigenvalues. So let's do that. This is not that is us. So now we have 3 eigenvalues, right? 2 plus 3j. J is just I, imaginary number. So 2 plus 3i, 2 minus 3i, and 2. What is asked is sum of the eigenvalues. So we can print np dot sum of eigenvalues and the product. So you get 6 plus 0j, which is just 6, and the product is 25.99999, which you, if you imagine very hard, it is very close to 26, so it is 26. Okay, and if you know the property of matrix, what's the sum of eigenvalues in terms of elements of matrix? Anyone? We can calculate the sum of eigenvalues without calculating the eigenvalues themselves, right? How do we do that? It's just trace. So we can print trace of A, which is given by, what was the, yeah, I can just write A dot trace, and this is A dot determinant, rather linarg. So the product of eigenvalues is determinant of A, which can be gotten using linarg dot det function. Okay, so let's just check if we are getting the correct answer. Oh, this has to be NP error, probably. Yeah, so the trace is 6, which is what we got as sum of eigenvalues, and the determinant is 26, which is what we got for product of eigenvalues. Okay, so that checks off. So sum of eigenvalues was 4, no, sorry, 6. It's a trace, right? So sum of diagonal elements 2 plus 2 plus 2, 6, and determinant is, well, it is 2 times, it's a block diagonal, right? So it's going to be 2 times 2, 3, minus 3, 2. So it is 2 times 2 into 2, 4, and plus 3 times 3, 9. So 2 times 13, which is 26. Okay. The reason I'm doing this in front of you is not to insult your intelligence, but again, if you encounter such questions in exam, you can do it by hand just to verify whether you are getting the correct answer. Okay. And then the last question, which is to calculate the determinant and maximum eigenvalue of this matrix. Okay, and again it's given linear.data for determinant and for eigenvalue I. Okay, so again let's just write A as np.array. Wow, thank you AI for typing out for me. And then determinant is going to be linear.det of A, and we have to round off to 2. Okay, so we are rounding off the determinant up to 2 places. That's one thing. And then we have to print the maximum eigenvalue, which is going to be the max of linear of A. But if we just write this one, then it gives eigenvalue as well as eigenvectors. So we just want the eigenvalues. So we put 0th. So it gives the first element, which is the array containing the eigenvalues. So, and then just take the real part and get the maximum value. Let's see if it works. Okay, so determinant is 17, and maximum eigenvalue is 7.5. And yeah, determinant is pretty easy, you can calculate on your own, I won't do it. And you can calculate eigenvalues as well, you can check it matches. Okay, so it is 17 and 7.5. Okay, so that's about it. Any questions from this? We did one question on bisection method and 3 on linear algebra. Any questions?
I just wanted to see your boundary value problem demonstration, whatever you have written. No? That was very nice to understand on that
Oh,
slide.
I haven't written actually, but
Oh,
I
is it
think
gone? Huh? Okay, okay, no problem. I'll see the recorded session.
no, I haven't actually done the shooting method. That's what you are saying, right?
Yeah, 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 yeah.
No, I haven't written the code for that because there was no issue.
Not code. You were explaining the
Ah,
shooting method.
yeah, that I have. Probably you were aware of
This
that.
one, that
Yeah.
yeah.
Okay. Let me just quickly explain. The idea is that if we take the example of pendulum, real pendulum, let's say you have a pendulum in front of you and your task is to get the pendulum exactly after 2 seconds at say 30 degrees. Then how do you do it in real life? Well, you push it with some velocity, say v0, and then see where it goes. So you pushed with v0 and maybe it reached 27 degree. So now you say that okay, v1 is going, maybe v0 was 3, so v1 will be 4 and v1 is 4, and that gave you 35 degree. But you wanted it to be 30 degree. So v0 was 3 and v1 was 4. So your v2 will be average of these two if you are doing bisection. 3.5. So check with 3.5 and maybe it gives 32 degree. Okay, so again you are overshooting. 32 degree. This is v2. Okay, so now what do you take as v3? It should be average of 3.5 and 3, right? So it's 3.5 plus 3 by 2, right? Because between these two is your actual target. So this will be 3.25. Okay, then again go for it. Maybe you get 30.5. So and then that means v4 will be 3.25, and again you overshot a little bit, right? So you got 30.5, you wanted 30, so again take average with this one. So 3.25, and what you got with 37 degree, which is 3 by 2, this will be 3.125. Okay, so what I'm trying to say is that you change your initial velocity and see what is happening. If you are overshooting, then reduce it. How do you reduce? Well, it depends on what method you are using. For bisection, you see where is the left point, yeah, the undershot point, and take the average of your least overshot and least undershot point, and again shoot it. If you undershoot, then the next interval is going to be the midpoint and the overshot point, because the target is somewhere here. And if you overshot, which means your target is here, then the next interval is going to be the undershot and the midpoint. Okay, so this way you keep on doing the bisection method. So if you know bisection method, it is exactly the same. It's just that the bisection, for bisection you have some variable x, right? So in this case the variable x becomes your initial speed, phi dot of 0. Okay, does that answer your question?
Yeah, thank you.
Yeah. Okay. Anyways, I'll upload the notes. Anybody else? Any questions? Okay, one point. Should we ask Professor Mahendra Verma to appear next session? This- Because by then it will be week 11 officially according to our schedule, but week 12 would also have been released, right? So if you want, I can ask him. Yes, Dipankar. What
Yes,
about
yes,
others?
we'll.
Yes. Okay.
Yes.
Pushpu, yes. Okay. All right. Then I'll ask him. Most likely he will come. If he's busy, then he might come in the week 12. But we'll communicate. Okay.
One more thing, this exam, they told some pattern like 5 questions will be there, but there will not be, will not get the environment, means will not get the Python, this thing, programming thing. Only we have to type in the window like that. It was told. So what exactly? Because our if we see our assignments, these are detailed Python questions, means
That's
programming questions, and high level maths is there. So if
okay.
with the virtual calculator, we may not be able to get the correct answers. Whatever calculator is provided on the online exam. So I just wanted to ask in what way we should prepare for that, or whether calculators will be allowed, or and
So
actually we have to do mathematics there, or we have to.
I think you should be allowed some calculator, but don't take my answer. Uh, Wait for 1 week and ask professor himself. Okay.
Okay, okay.
And he would probably know. And if he doesn't know, then we can ask the official people, or he can ask. And that way you can get the exact information. Because I'm not involved in the exam process.
Okay.
Okay.
Thank
Yeah.
you.
Anybody else?
One more thing.
Okay.
Yeah. Actually, now we solve the assignment as like last assignment question that today we asked that about the question number 5.
Yeah.
That is get wrong options over there.
Yeah.
So it's like if whatever the solution we got it only the answers for that solution,
Right.
only the option A, B, C. Instead of that, if you provide the answer assignment answers in the form of if there is a coding is in there. So
Mm-hmm.
if you provide us the code, then we can
Okay.
find out what is wrong in our code also after
Yeah.
the assignment. I'm not saying about the current one,
I
which is
understand.
like which we already solved it and we got the wrong thing. It is
Mm-hmm.
not a matter, but later when we decide that it is get wrong, and then you have to evaluate and again cancel it or whatever the process. Decide that if you provide the code for
Mm-hmm.
that answers, then we can check our code also. Some
Yeah.
shortcuts where they have used, we can use that one also.
Right.
And we are new for the Python, so actually I'm new in a Python, so
Mm-hmm.
I'm using that little bit long methods. So some
Yeah.
shortcut will be provided in that method, so it is better for the people like us.
Mm-hmm.
So
Yeah.
in the answer, they should provide us the codes.
Okay. So the thing is, questions are made by someone else, but they have started sharing the solutions with me. So I'll first ask them if they can upload directly the solution. Of course, after the assignment is closed, directly to the course content, maybe somewhere here. If that's not possible, and if they allow me to share the solutions, then I can put it in my drive link. That should also work, right?
Yes, yes.
Yeah. So, but I'll have to ask. So next week onwards, which will be just 2 weeks, but what can we do? You will have solutions. Okay.
Yeah, the assignment is already gone, so
Hmm.
if you have the solutions and if they give the permission, you can put the previous assignment answers in code also.
Yeah. So I started getting from week 10, I think. So I have this week's solutions and probably next week's as well. Yeah. But I cannot directly put it right now because I haven't prepared the solution. So I'll have to ask professor and those TS. Okay.
Okay, no issue. Thank you.
Yeah. Anyone else?
Previous assignment was that question where 7 questions only were there. That is that I want, means if code is provided, that will be the better thing. I
Uh,
think assignment 9 only. I think it was very
9, right? Yeah.
with 7 questions. Yeah,
Yeah.
that
That's one.
that last 3 questions.
So
if we get.
for last one, for example, you already have the code because it's same as my code or uh, his code, Agrim's code. So he takes sessions on Sunday, right? So
Yeah.
you just have to change the parameters, and this is, I think, different. Maybe it's also the same thing, 1D wave. Most likely it's the same thing. So if you look at the form of the problems, it's almost same. You just have to change the parameters. But still, there could be some problems which are not solved at all. For example, this time there are some questions on other questions on shooting methods or something. I don't know. Let me check. This is bisection Newton-Raphson, for example. But I did not have Newton-Raphson in my thing. So for that you may need the solution. So I'll ask them because they are anyways solving it. So it's only fair that solution be shared. If they don't allow, then I'll solve on my behalf and then I'll share it. Okay. Does that sound fair?
Yeah, thank you.
Okay. Okay, then let's meet next week and hopefully professor will be kind enough to join us. If not, then we'll just go on as usual. Okay. Chalo. Bye bye everyone.
Thank you.